In section 2, we are going to talk about significance tests for population proportions. So what a significance test is, it compares a claim that a set of observed data is not the result of chance variation, but due to a specific cause. So we are comparing a null hypothesis called HO to an alternative hypothesis HA that asks the question, how likely is it to get a result like this just by chance when the null hypothesis is true? So there's a couple very important things about hypothesis tests when you are conducting a problem. The first is that hypotheses are always developed before a study is conducted. So we can't adjust our hypotheses after we have already gathered data because then it would be biased. The second thing is that our data will be above or below the claim, but if we started off not knowing which direction the data would trend, we have to keep running the test that way because next time it could trend in the other direction. So both of those are reasons why we develop our hypotheses ahead of time. So there are two different types of hypothesis tests. The first one is a one-sided hypothesis test, and there's two different ways you can do a one-sided hypothesis test. The one is that your null hypothesis would be equal to whatever proportion you state, and the alternative would be that it tends in a specific direction, either less than or greater than that initial amount. So because we are looking in one direction, they're called one-sided. So they are one-sided because we are looking at one side of our null hypothesis. And hypotheses they use the same value for the null hypothesis and the alternative hypothesis. So a null hypothesis is always equal to. So whatever your proportion is, we will always state that the null hypothesis is equal to it. The alternative hypothesis is set above or below that same value. And then our hypotheses are based on our population parameter P. So hypotheses have to be based off of the population parameter. We will use a sample proportion p hat, but not in the writing of our hypotheses. The second type of hypothesis is called a two-sided hypothesis, and it is called a two-sided hypothesis test because we are looking for a difference in the claim, and we're not sure in which direction it will be different, just that it is not equal to our null hypothesis. So the alternative hypothesis is always does not equal in this case. So this is just an example of the two hypotheses we already did in our one-sided test, but the alternative could be that it's not equal to whatever that claim is. We don't know if it's bigger or smaller. We just think that it isn't what we already claimed. So when we are performing a hypothesis test, to make the decision about whether or not we have enough evidence against our null hypothesis, we have to calculate something called a p-value. And a p-value is a probability that is computed assuming your null hypothesis is true, that your statistic, p hat, would take a value as extreme or more extreme than the one actually observed in the direction specified by the alternative hypothesis. So what that is basically saying is the p-value is how likely you get the p hat that you calculated, or something smaller if your alternative hypothesis is less than, or something greater if your alternative hypothesis is greater than. So when we are calculating our p-value, we use our sample statistic p hat and our null hypothesis. And we do calculate a z-score to figure out the difference between what we observed and what our claim is. And then we are going to use normal CDF to calculate the probability that we get that value or something more extreme and make a decision on if that probability is low enough to say that it is unlikely to occur by chance. And how we determine if it's low enough is something called a significance level. So now we're going to talk about what a significance level is. So a significance level is denoted by the Greek letter alpha. So it's your like fish A. And it is also set before a test. We are going to talk about more in section 3 about how your significance level is chosen. There's always a few factors that go into it, but it's either given in the problem or it's always assumed to be a specific value. And if it's not given to you in a problem, we always assume that alpha is 5%. And we'll talk about more reason in section 3 on why that is. So there are 2 decisions we have to make based on alpha. If our p-value is smaller than alpha, so as a formula, that would be p-value less than alpha. That means that the results of the study are statistically significant and the probability of the event occurring by chance is so low that it is not due to chance variation. What that means is that your p-hat that you calculated is low enough to say that the population proportion, whatever it stated, is not actually accurate. So in that case, what we do is we reject our null hypothesis and conclude that there is convincing evidence in favor of the alternative. Okay. On the reverse side of things, we could have then that our p-value is greater than alpha. So p-value greater than alpha. So we say the exact opposite that we would say for when it's less than. So the results of the study are not statistically significant and the difference in p and p-hat is due to chance variation. What that means is it just happened that our p-hat was either big enough or it was just slightly different from the null hypothesis by chance. That if I were to do it again, that it would likely be closer to my hypothesis and it was just by chance that I got something that was different. So when this happens, we say we fail to reject the null hypothesis and we conclude that there's not enough convincing evidence in favor of the alternative. It is very important here that when we fail to reject the null hypothesis, that does not mean we accept the null hypothesis. We never actually say the null hypothesis is true. We either have enough evidence in favor of it or we don't, we either have enough evidence in favor of the alternative or we don't have enough evidence in favor of the alternative. A hypothesis test does not actually prove that the null hypothesis is true, which is a very important thing when discussing hypothesis tests, is that we're not actually proving anything. We're trying to gather evidence in favor of the alternative hypothesis, but we're not actually proving the null hypothesis true. So there are three very common significance levels: 0.01, 0.05, and 0.10, which, if you think back to the normal curve, and you're talking about the area above or below a critical value, we're talking about the area being 1%, 5%, or 10%. So we don't use large alphas because our probabilities are going to be typically small. So we want to choose an alpha in such a way that we're not rejecting when we shouldn't have, or failing to reject when we shouldn't have. And again, this is something that we're going to go into more detail in section 3 on how do you choose your significance level so you're making the right decision in your significance test. So in order to calculate our p-value, we have to do our test statistic. And the test statistic is just a z-score. So it's called a z-test statistic, and it is equal to your test statistic b hat minus whatever value you get from your null hypothesis p naught over the square root of p naught times 1 minus p naught over n. So it is important here that we do use the proportion from your hypotheses, because it is a claim about the population. So we have to use it when calculating our standard deviation. So when we calculate our test statistic, we're doing our sample proportion, we're subtracting our population proportion from it, from our hypotheses, and we're calculating the standard deviation based on the hypothesis. Okay. Now, when we then calculate our p-value, all right, based on our alternative hypothesis, that determines if we're finding the probability above or the probability below. So if you remember back to normal curves, okay, if our alternative hypothesis is that we actually want to be less than. So in a normal curve, our mean is 0. Our z-score, if we are below our null hypothesis, our z-score would be negative. And our probability would be the area below. So this would be our p-value, would be the area below. So it's how likely are you to get something below that null hypothesis. If the alternative hypothesis is that you are not equal, okay, so our mean is 0, we could be above or we could be below. So in this case, our test statistic could be positive or it could be negative. And our p-value actually has to be the likelihood that it is in either of these. So the p-value actually falls in one of two places. So when we go to calculate it in the computer and we do normal CDF, in the calculator I should say, and we do normal CDF, that's the probability of it only falling in the area that we have looked at. So if our z-score is positive, when we do normal CDF, it's the likelihood that it's only in the positive direction, and we want to account for both. So in this case, when we calculate p-value, we have to double the p-value from the calculator. Because we could be in either. And then if our alternative hypothesis is that we're actually greater than, we have our mean, our test statistic is going to be positive, and we're looking at the probability that we have an area above, and this would be where our p-value falls. So let's go ahead and look at an example. So Alan reads a report that says 80% of U.S. high school students have a computer at home. He believes the proportion is smaller than 0.8 at his high school. He chooses an SRS of 60 students and records whether they have a computer at home. He wants to test this at a 5% significance level. In his SRS, 41 of the students have a computer at home. So the first thing you do when you are reading a problem is write your hypotheses. So you have to pick out the information about the population claim and the information that's going to give you your alternative hypothesis. So our null hypothesis is based off the fact that the report says 80% of high school students have a computer at home, and he believes the proportion is smaller. That is going to give us our null and alternative hypotheses. So our null hypothesis is going to be that P is equal to 0.80 because it's always equal. The alternative hypothesis is going to be that P is less than 0.80 because that would be smaller. The next thing we want to do is calculate our P hat. So our number of yeses is 41 over our sample size of 60, which is going to be 0.683 repeating. So I'm going to go 4 decimals, 0.6833. And again, P hat is not guaranteed to be a nice decimal, so we don't want to round too early for the calculating of our test statistics. We want our z-score to be as accurate as possible. So when we calculate our test statistic, we're going to do 0.6833 minus our null hypothesis, 0.8, over the square root of 0.8 times 1 minus 0.8 all over 60, which becomes negative 2.26. Now we go ahead and do normal CDF. So our lower bound is going to be negative 1E99. Our upper bound will be negative 2.26. And because we've calculated a z-score, our mean is 0 and our standard deviation is 1. A nice thing about hypothesis tests is that if your z-score is negative, your lower bound is always negative 1E989 and your upper bound is always your z-score. And if it's positive, the lower bound is your z-score and the upper bound is positive 1E99. We're going to get 0.0119. Once we have calculated our probability, we now compare it to our alpha. So this is our p-value. It equals 0.0119, which is less than our alpha, which is 0.05. And if our p-value is less than alpha, then our conclusion is we reject our null hypothesis. So you do have to specifically state after you've compared your p-value to alpha, whether you're rejecting or failing to reject your null hypothesis. And then that last thing that we have to do is write our sentence. And similarly to the confidence intervals, the sentence for a hypothesis test is very similar based on your conclusion. So we can say there is enough evidence to show the true proportion of high school students with a computer at home is less than 80%. So depending on whether or not you reject or fail to reject, it's either there is or there is not enough evidence to show that the true proportion, and then whatever your scenario is, and then you're basically stating your alternative hypothesis after that. For our next example, we have that a coffee shop claims that 60% of its customers prefer iced coffee over hot coffee. A competitor suspects that this proportion might have changed due to recent changes in the shop's drink menu. To test this, the competitor randomly surveys 150 customers who visit the shop in the past week and finds that 78 of them say they prefer iced coffee. At the 5% level of significance, is there enough evidence to suggest that the proportion of customers who prefer iced coffee is different from 60%? So for our null hypothesis, our P is going to be the 60% because that's what they claim is the proportion. Now, in this case, in the wording of the problem, it says that the competitor suspects this proportion might have changed. So when you don't have any specific words that say greater than or less than, that means your alternative hypothesis is does not equal. So we're not specifically saying it's bigger or smaller than 60%. We're just saying that we don't think it's 60% anymore. So our alternative hypothesis is does not equal. Our P hat is going to be 78 over 150, which is 0.52. So for our test statistic, we have 0.52 minus 0.60 over the square root of 0.60 times 1 is minus 0.60 all over 150. Now, obviously, even though our alternative hypothesis is does not equal, we are going to get either a p hat that's bigger or smaller. And our z-score ends up being -2. So when our alternative hypothesis is does not equal, and you calculate your z-score, and you're trying to determine does it go in as the lower bound or the upper bound, it is based on whether or not your z-score is positive or negative. So for normal CDF, because our test statistic was negative, our lower bound is -1E99, and our upper bound is the -2, with our mean of 0 and our standard deviation of 1. If we had gotten a p hat greater and our test statistic had then been positive, our lower bound would have been the z-score and the upper bound would have been 1E99. So we're going to get 0.0228. Now, because my alternative hypothesis is does not equal, this is not my p-value. You have to remember that for a does not equal, my p-value has to be a combined probability that it could have been below or above. So for my p-value, I actually have to do 2 times 0.0228. And it becomes 0.0456, which is less than 0.05. So I am still rejecting my null hypothesis. It hasn't changed my conclusion, but for other problems, that test statistic might be a number, give you a probability that when doubled is high enough to then change your conclusion. So you have to remember, when the alternative hypothesis does not equal, double the probability you get after normal CDF. Then for our sentence, we say there is enough evidence to show the true proportion of customers who prefer iced coffee is not 60%. For our next example, we have that a tutoring company claims that historically 70% of its students who use their services pass a standardized math exam. After introducing a new online tutoring program, they want to know if the pass rate has increased. To test this, they randomly select 120 students who used the new program. Of those students, 94 passed the exam. At the 0.01 significance level, is there sufficient evidence to conclude that the proportion of students who pass the exam using the new program is greater than 70%? So for our null hypothesis, they claim that 70% of students pass, so it's going to be that P equals 0.70, and we are trying to determine if the pass rate has increased and is now greater than 70%. So our alternative hypothesis is that P is greater than 0.70. So for our P hat, we'll do 94 over 120, which is 0.783 repeating. So I'm going to do 7833. You can also leave your P hat when it's not an exact decimal as a fraction if you want to calculate your test statistic a little bit more accurately. So as a fraction, 94 over 120 is 47 over 60. So you can always use that fraction when calculating your test statistic if you want to get the most accurate test statistic that you can. And I'm going to calculate both so you can see what they are for this next one. So for my test statistic, we'll get 0.7833 minus 0.70 all over the square root of 0.70 times 1 minus 0.70 all over 120. And we get 1.99. And if I were to calculate the z-score or the z-test statistic with the 47 over 60, I actually end up getting the same number to 2 decimal places. It's still 1.99. So rounding to 4 decimals still gives you an accurate test statistic. So for normal CDF, our lower bound is going to be 1.99 and our upper bound is going to be the 1E99. Mean of 0, standard deviation of 1. The other thing I didn't do in these notes is check conditions. So technically speaking, when you're performing a significance test, just like with a confidence interval, the conditions for random, independent, and normal all have to be met. Which again, I am not going to require you to do on a problem, but I still expect you to know the conditions. So it's the exact same conditions as a confidence interval. They have not changed for a significance test. So we end up with 0.0233 as our probability. So our p-value of 0.0233 is greater than our alpha of 0.01. So because our p-value is greater, we are going to fail to reject our null hypothesis. So the only thing that changes in the writing of our sentence is we now say we do not have enough evidence. So, or there is not enough evidence. So there is not enough evidence to show the true proportion of students who pass the exam is greater than 70%. So we can see here how choosing your significance level affects your conclusion. Because if I changed my significance level to 0.05, that would change my conclusion because 0.0233 is less than 0.05. And like I said, we'll talk about more in section 3 about choosing a significance level and why it's so important and why the most common one is 0.05. So the last thing we're going to talk about is the similarities between a two-sided significance test and a confidence interval. So confidence intervals and significance tests actually go hand in hand with each other, especially when you're doing a two-sided significance test and then a confidence interval that is the remaining percentage. So for example, if you're doing a two-sided significance test, so it does not equal alternative hypothesis and your alpha is 0.05, and your confidence interval is 95%, they are going to give you similar information about the population parameter. And if you reject the null hypothesis for the significance test, then your confidence interval at your percent actually will not contain the hypothesized value. And if you fail to reject, then the confidence interval will contain. So we're going to look at this through an example and kind of show how they support each other. So we have a polling organization wants to estimate the proportion of voters in a city who support a new public transportation initiative. An SRS of 400 voters is taken and 220 of them say they support the initiative, assume all conditions are met. So we're going to construct our 95% confidence interval for our true proportion of supporters. So our critical value for a 95% confidence interval is 1.96. And then our p-hat is going to be 220 over 400. Which is 0.55. So when I do my interval, it'd be 0.55 plus or minus 1.96 times the square root of 0.55 times 1 minus 0.55 all over 400. So when I go ahead and do my 1.96 times the square root of 0.55 times 1 minus 0.55 all over 400, we're going to get 0.55 plus or minus 0.0488, which gives us the interval 0.5012 to 0.5988. Okay. So if for my hypothesis test, we had that the city states 50% of voters are in favor of the new public transportation initiative, and we use our 5% level of significance, we can determine if the proportion is different than the city stated. So our null hypothesis would be that P equals 0.5, and our alternative would be that P does not equal 0.5. We have the same p-hat of 0.55. When we calculate our test statistic, we do 0.55 minus 0.5 all over square root of 0.5 times 1 minus 0.5 all over 400. which gives us 2. So we do normal CDF. Our lower bound is 2, upper bound 1E99, mean of 0, standard deviation of 1. And we get 0.0228, which again, to calculate our p-value, we have to remember to double. So we do 2 times 0.0228. Which gives us 0.0456, which is less than our alpha, so we would reject the null hypothesis. Which I know I should be doing because my confidence interval contained my proportion of 0.50. So do your results from the confidence interval and significance tests support each other? So the answer would be yes, because the significance test conclusion was reject, and the confidence interval contained P0, which was 0.50. And this is specific to two-sided hypothesis tests. It does not work out if you're doing a one-sided hypothesis test exactly, because with one-sided hypothesis tests, we're only looking in one direction. So it's not that your alpha and your confidence level have to add to 100. So for it does not equal, because we want the area above and below, if we think back to our normal curve, right, we can have your negative z, your positive z, you're the combined area below. My confidence is in the middle, like 95%. Each area above and below would be the 2.5%, which we have to add together to give us our alpha of 5%. When we do a one-sided hypothesis test, we only care about one area. So if I were specifically doing greater than, my area would be 2.5% that would be looking at. So the confidence level I want to look at would actually be 1 minus 2.5%, which is 97.5. So if you're doing a one-sided, it's not alpha and then as a percent and then the remaining percent, it's technically alpha and then half of it that's left. So it's like the alpha with the percent and not the 100 times 1 minus alpha percent. So it's not those two. Let me know if you have any questions about performing a hypothesis test for proportions, whether that's writing the hypotheses, calculating your test statistic, calculating p-value, making a conclusion, or the sentence.